I'm trying to do the Bitcoin life, like trying to save as much money so I can stack all the time. Uh, but I live in San Diego, and San Diego is super crazy expensive. And this is what you get. I just like just directly on the street. I need probably to put some soundproof panels or something all around me so you guys don't hear. But yeah, so we usually meet on Wednesday to talk about the book scale. I'm still working. I'm preparing like a series of lectures where maybe we can meet and go through the lectures, and I'm starting next week. But I did all this work that is kind of relevant because it's about scale. And if you guys don't know, because I see a lot of new names, so welcome, guys, first of all. By the way, you can talk. You're free to talk if you want to participate to the chat. Um, and in fact, saving face if you want to record it because we're going to discuss some interesting stuff.
Yep, I got it
Uh,
going.
and so one of the things you can do, you can click if you're sorry if you guys are already familiar with this, but click on the little bubble near the voice channel, and then two things are going to appear. There is this big window with all our names, and at a certain point I will share my screen so you can actually see my screen. But also there is a chat window. So if you don't feel like talking because maybe you're in a loud place like a coffee place or whatever, you can always write in the chat. You can write questions or make comments. It's basically supposed to be a conversation. These our meetings are. So you're welcome to ask questions. If you want to talk, I'd rather there to do that because we can hear your voice and get to know each other. And you should be able simply to talk. Is a voice activated microphone. Double check. I had to do it myself today because if you charge your phone or if you use other apps many times, Discord wants you to reset everything. So what you can do, you can go all the way down, and there is that little gear, right? You see the little gear near the headphone, near the microphone, and then you click on user settings. You go to the place where it says, some the left, there are all these choices. One says voice and video, and when you click on that and you choose, the relevant type fonts, the one that you're wearing, or the microphone that you want to use. Um, did I lose Discord?
No, no,
No, okay.
no,
I
you're
thought
here.
yeah, I'm still here. I don't see the icon for Discord. Okay. Where is it? That is weird. Okay. Perfect. Um, yeah, so that is the idea. So, and we can talk about anything, but I wanted to show you some of this work that I'm doing. And so basically, there is always the doubt when we do these graphs, right? When we do our classical, and in a sense, okay, I can show you. Let me show you the screen. Okay. So this is some of the work that I did before, and it's basically showing all these power laws, right? That I have found before. I have found basically 6 different power laws. I don't know if people realize that, when they think that there is one and they want to break one. Well, the classical one that everybody's familiar is the one at the third level, right? In the panel below, that is basically price versus time, right? You have price versus time, um, and you measure the slope, you do a regression. And by the way, I hope everybody understand it's not really a straight line, right? It's if I plotted in a linear graph where I have a price, I have a normal price, I have a normal time, it will look like a J. It's like a very fast growing function, because see when when we look at the exponent, the slope of it graph is basically how fast it's growing, like the power, right? When people say, oh, the price went parabolic, really usually they mean exponential, but if I meant parabolic, it would mean like a parabola, right? And a parabola is square. We are talking about something close to 6, so it's much faster than a parabola. So it's really like a J, you know. The reason why we do it in this way using the log is because people, humans like straight lines. So these curves, these things that are like curved, it doesn't matter what it is, if it is a square, if it is a cube, if it is a 6, if it is a relationship, it looks like y equal x to some power, whatever the power is, it's going to look always like a straight line. And then the slope is going to give you the power. And you can see all of them have different powers, right? For example, addresses, if you do it in terms of time, has the power of 3.1 something. And if you plot price versus addresses, is also a power law. And the slope is 1.77. If you do price versus time, you get 5.65, something close to that, close to 5.7. Let's round it up to 6, close to 6. And then you can do the other relationship. You can do price versus hash rate, and that relationship is basically like 1/2, close to 1/2. You can do hash rate versus addresses, and that relationship, versus time, that relationship is close to 12. Um, you can do it addresses versus hash rate, and you get 0.25, and so on. So they are all related to each other. They are all power laws. Now, what does it mean, right? Because in these on Thursday, we usually read this book. If you guys didn't get the book, please get it, because it really. And I'm going to write a similar book. I'm going to make I'm going to show how all this stuff actually applies to Bitcoin. It will be more Bitcoin focused, but this book really does an amazing job in showing and posting it in the chat window. So get the book, get maybe even a Kindle version of the audiobook. It's better if you get. Sometimes we have deals, the Kindle and the audiobook, because we are going through the book, and so it's nice if you can read it. Actually, we'll have lectures about these books in the next few Thursdays. But basically, it's the idea of they call it universal laws, because in physics we really are fixated with this thing where we want to find analogies between different phenomena. When we find that, we are up, we are super happy. It is really what physics is all about. We want to find how things relate to each other, right? And some of these phenomena are called universal because they apply to everything. They apply to how planets move. We apply to how biological system works. We apply to how people relate to each other. It's really, really universal. And one of the most universal phenomena is this idea of power laws, because power laws, scaling, this idea, what is scaling? Because I know that some people get turned off because they hear these technical terms and they think, what, that has anything to do with Bitcoin? I want not normal stuff. I want you to connect two dots and tell me, the golden cross, stuff like that. People are used to stuff like that, and they get all excited with type of post, get like, 30,000 likes, because people don't understand. They don't understand what is important, what is not, right? Because they didn't have. Also, they don't teach this kind of things in school. They should. They should take a book like Scale and read it. People will get excited, instead of teaching a lot of BS. Because it's a very incredible book, because it shows you how everything works, all around us. There is this idea. Because I think about, right, we as humans are in the middle of reality, right? We have all these very small little things called particles that are very, very small, right? They are just to give you an idea, the atom is about one one tenth of a billion of a meter. So 10 to the minus 10 meters, right? Zero with 90 plus one, right? 0.090 is one. 1/10 of a billion of a meter. And a meter is like a yard, right? For our meter challenge listeners from the US. But it's basically the meter. If you're thinking about scale, right? The meter, and this is why we used it. This is why we came up with this idea of a meter. People did not, in ancient time, what did they, anybody knows what in ancient times people were using to measure things? What did they use? What are typical measures that they use before they did the meters? Anybody can, if you want to, you can write it in the chat or answer. What are, for example, what are the Romans used? Like when they were measuring distances and things like that.
I don't know about small distances, but didn't sailors used to use like leagues or something like that?
Yeah, so all the Romans we use miles, right? Miles. What is miles? Miles comes from mille. Mille is thousand. Like a millennial. Like the word in English. A lot of English words derive from Latin. Millennial. In Italy, we still say mille. That means thousand. And it was thousand steps. It was thousand steps. This is literally what it was. Now, of course, at a certain point, they codified it like, okay, this is what it is. But Romans, in fact, it's funny because one time I read an article where they compared Roman miles with English miles, and it turns out the miles for Romans were smaller because they were small Italian dudes like me. And so their steps were smaller in average, right? Of course, once in a while they had a taller individual. At a certain point, they recruited all these German people in their army. But in general, they were, like smaller also because of nutrition. In fact, probably they were smaller than Italian people are right now. Um, and so they will use their body, right? They will use their body. They will use a arm, the foot, of a step, like 1,000 steps. It's the distance, right? For then you can have fractions of that. So people use things that they could handle, even weights, right? Things that they could hold in their hand, like the kilos, right, of a pound. There are things that you literally can hold in your hand because humans became the measure of everything, right? And this is how we make sense of our world, and we try to measure it. It's based on the size of human beings. Uh, but it's interesting because we are kind of in the middle, right? Because these very, very small particles, these are subatomic world. Now, if you go to the subatomic particle, you go 100,000 smaller because the atom is 1 billionth, right? 1/10 of a billion of a meter. The nucleus of an atom is 10 to the minus 15, not 10 to the minus 10. So the nucleus is 100,000 times smaller than the atom itself. Can you imagine? Now we don't know because when every particle is made, by there are elementary particles like electrons. We don't know how big is the electron. Probably, like we tend to think like it is like a dot, but it's probably impossible. But it's like a dot, like physically, but we don't have a clue. Like it's very difficult to measure the size of an electron because all kind of crazy things happen. There are all these virtual particles that stick to the electron. Um, there are some elementary particles we don't know how big they are, and then same thing with the quarks, okay, because they all interact with each other. But we think there is like a limit, the smallest possible. There are some theoretical reasons why we think there is not like an infinitesimal size. Anybody knows what is the smallest possible scale? So these are called scales, right? So are called scales, are order of magnitude, right? So we say, you can even write it down. 10 to the minus 10 is the atom. 10 to the minus 15 is the scale of subatomic particles, um, and all these in meters because scientists use meters. But anybody knows what is the smallest possible scale? Is there a small possible scale? It's do we go? Can we go to 10 to the minus 50 meters or something like that? Anybody knows? Don't be shy.
I have no idea.
So do you think that we can go all the way to the smallest possible number, like 10 to minus 50, or maybe there is like a smallest possible scale?
To be honest, I have no idea. I haven't actually even researched that before. Like, but I understand that we can basically measure what we can see almost in a microscope. So that's about as
Well,
knowledgeable I
with
am on the
subatomic
subject.
particles, you don't even do that. Like
Mm.
what you do, you smash things. Literally, that is like, imagine if you wanted to understand what is inside a watch. Physics is really cool. It really is going to be, is always my first love and will always be. But basically, this is how we do it because we don't have microscopes. But we are starting to go to a level where we started to take pictures of things like maybe atom scales. And there are all kind of tricks that people use. It's really complicated. It's not that easy. It's not as simple as, oh, okay, I'm going to look at through a microscope. But microscopes, they go, maybe 1,000 or 10,000. Um, I don't remember. We have these electro microscopes that can go to very, very small scale, but not these scales. When we study things at that scale, basically we take, like, imagine you have a watch, you want to understand what the watch is made, and you say, okay, let me take this watch, and then you throw it against the wall. You throw it literally against the wall. Or actually, better, you have another dude and say, hey, let's smash these two watches, and you have to be very precise because you're throwing it in the air and the two watches need to collide, and so you do it exactly like that. You collide it, and you do it many, many times because you're not sure what is going on. Because part of what is going on, imagine this, imagine when you smash the watches, that is already crazy, right? Because you're hoping to know what is inside the watch by taking pictures after the collision, and you're seeing all these parts that are coming out, and you say, oh, okay, this is what it's made of because all these components are coming out. But imagine that the energy of a collision, when you're smashing things, creates out of nothing more components. There are like extra springs, extra components of a watch that are added to the original one because some of the energy is getting transformed into matter, and so you have to figure out what was really there before and what is created from scratch, and plus it's all indirect because you're taking traces, you're seeing where the different components are moving, and by how much of the bend or the trajectory they take, you derive what they are, right? And all the measurement at this scale has to do mostly with the physics involved, like how strong the interactions are. It's all theoretical. I mean, we don't really see at these very, very small scales. It's all calculated through what we think we understand about the laws involved at these scales. Now, the smallest possible scale, and it's all about theoretical physics. There are a sequence of steps and reasoning why we think is the case. We think that there is like a fundamental scale at which you cannot really go below it. It's 10 to the minus 33 meters. So it basically like says the world is, almost made of pixels. There are these little pixels, and these are the smallest possible pixels. Now, if you go below that, everything became fuzzy, and you cannot, like even the laws of physics start to go crazy. And so maybe there is some reality below that, but we don't know even how to think about it, or our understanding of physics breaks down. And so we consider it almost like a fundamental scale. It's called the Planck scale after physicist called Planck. And that is the smallest possible, as far as we know right now, scales for size. There is no smaller than that. It's the word that's literally pixelated. It is really weird, right? Many people don't know about that, but it's really curious, very interesting. Oh, and but if we cannot really even explore really directly 10 to the minus 15, we are talking about many orders, right? Almost like uh, 18 orders of magnitude below that. It's completely absurd, like we don't know what is between that theoretical scale and the scales of subatomic particles. Are there other things there, or is just emptiness? We have absolutely no clue, because we know a lot of stuff, but there are a lot of other stuff that we don't know. It sounds crazy, right? That you can go all the way down to very, very small scales, but um, and the one that we experience right now so far, we are not found anything smaller than that. Um, the subatomic particles. But we don't even have the tools, because to explore these other scales, we will need like when I say we smash these things, we do it in these particle accelerators, and bigger they are, more energy you get, right? And right now, some of them are like many, many kilometers wide, but we will need something almost like the size of a galaxy to go all the way and explore these very, very small scales. So we don't have even the technology. Maybe in the future, but right now, there is this big gap. But this just gave you a feeling of this idea of scale, right? Then, you have things like cells, that are maybe on the order of hundreds of thousands of meters. There are different type of cells. And so very small little things. There is this scale called nano. That means 10 to the minus 9. That is kind of there is this field called nanotechnology that helps to operate at that scale. It is just a little bit above the atoms, and so things like molecules, etc. So you could maybe one day we could have machines that can operate at these scales, and we can assemble things molecule by molecule, and you could make all kind of crazy stuff that both positive or negative. But we will have a level of control about matter that will be incredible. You could make like you probably saw some science fiction movie, right? When we say, "Oh, this is a nanotech suit," you could make a suit that is built like an armor, like built by molecule. You put it together to this nanotech little bots that you have control of, and that a suit like that will be basically without any kinks or any defect, and will be almost indestructible. They show that often in Marvel movies, right? They say, "Oh,
Mm-hmm.
I made like Iron Man. It's supposed to have like nanotech available that will be crazy, because it will revolutionize everything. You literally could take a bath, a bathtub. You go put there some rubber, you put some sand, for the glass. You put all the fundamental materials. Other can even be extracted from the air. Some metal, some scrap stuff. Then you throw like a little vial of these nanobots. You mix it together, and you come back after a few hours, 6 7 hours, and you have a car. These nanobots assembled a car for you, perfect, from all these fundamental material. It would be fantastic if one day we will be able to do that. But then you go up, and finally you arrive to the level humans. Then we go higher than that, right? We are talking about planets, like houses, of course, mountains, and planet. Like anybody has a clue of how big a planet is in comparison with a human? How big is the Earth? What is the radius of the Earth? Anybody?
Sorry, I'm not sure the protocol for just asking a question. Can I just ask a
Sure, yeah,
question?
of course, yeah. Anybody
Sorry.
can interrupt at any moment.
Yeah. Okay, thanks. Firstly, I'd just like to say your charts are really fantastic. I do a lot of research on this along with my day job. So I just curious. So I guess yeah, there's sort of no question that the data supports the power law model. But the thing is, I noticed money or debt matched quite closely with a Weibull S curve.
Mm-hmm.
And his explanation was that we were still sort of at the early stages before the knee, and that's why
Right.
it also matched. Yeah. So, what are your thoughts on that? Like,
Yeah. So the Weibull is a kind of a variation of a team because there are different types. It's this kind of class of functions that are called logistic functions, and some of them are exponential, like these are the famous S curves. Like we start like an exponential, and then basically they are supposed to represent adoption, right? So uh, it's all kind of like an exponential, but basically we have some kind of saturation effect, right? So they grow, and then they seem faster, but it's not that anything really changes. It's mostly our eyes that start to pick up the exponential behavior that in the beginning looks flat to us, because exponential depends how fast it goes, right? A very, very slow exponential can look like flat. But then eventually the exponential picks up because it goes as things are as time passes by. The changes looks bigger to our eyes because we are not used to non-linear things, and then eventually this kind of like a J curve, like a J, like a hockey stick, starts to saturate, right, and flatten out. Now, uh, Bitcoin doesn't do that. Like you can look up addresses, for example, as a proxy for adoption because it's one of the. I tend, as a physicist, we like to focus on things we can measure. We call them observable. So addresses is the most direct observable that we have in terms of adoption. Some kind of activity in the network that is associated with how active a network is. So this is why I have these addresses graph in what I'm sharing, and this to me is the closest measure of adoption we have. And you can see it's basically a power law, right? It's not perfect, but it's approximated very well by a power law. Now, so it's not an S curve, absolutely not. Like I get mad when there was one time Fidelity macro director, some big guy that probably paid hundreds of thousands of dollars, and he was spewing BS. You are misinforming people. You don't look at the data. You don't understand the data. And I'm sorry, I think really, literally, me and few of these other guys from the power law, we are literally the only one that understand. I don't know. Maybe there are some hidden people somewhere that work for some fund or whatever. But when I see Fidelity, right, these guys should be experts, and they say, "Oh, it's an S curve." They were claiming that adoption for Bitcoin is a S curve. Based on the heck what? They were taking the addresses, in fact, and they were fitting it with something that they thought worked, like because they think is like technologies. It doesn't. The best fit is a power law. I don't know why they do this. I don't know. I have no clue. Maybe because it's simpler for them. These are supposed to be, they are PhDs, they are experts, and they say bullshit. And I know it sounds arrogant. They say, who are you, when these guys have so much money available. But what about the Weibull? The Weibull is another possible model where it starts like a power law and then it tapers off. And that is not excluded by the data. Like you can see, it's a power law, but we could modify it and make it like a Weibull. And I did a work like that because people don't not realize how much work I did. And at a certain point, I want to create like a website where I systematically, beside the book that I'm working on the book, and I'm going to also, I'm in the process of write scientific papers that I want to send to peer review journal. But I want a place where, Bitcoiners can go and they see all the work I did. There is I don't know if you guys are subscribed to our webpage. We have like a newsletter, but I wrote this article, because I'm trying to write a series of articles. This one is called Modeling Bitcoin Growth with Network Theory. So what I did in this article, okay, and I can show you the graph, the relevant graph. I took this very, very general model. So basically, the idea is that we think Bitcoin is a network, right? And it's a social network. It's a network of machines, machine and people interacting with each other. So it's a place where there are units that make decisions, like some processing of information, like the Bitcoiners, and then we have the machines, that they do all the hash rate, etc., and they interact with each other. So I just posted this graph. So I posted the article if you want to read it, and I posted the relevant graph. So in this relevant graph, you see these complicated equations, but really they are not that complicated if one knows a little bit of math. But you see the top equation, right? You see addresses, you see price, then you see that top equation. What that is called a differential equation. It's an equation that describe change, because it's very, very physics-like. We do that a lot in physics when we want to describe the motion of a particle, the motion of a planet. We write differential equation. In fact, as a physicist, you need to take several classes on differential equations. There are what are called partial differential equations, when you have more than one quantity that changes at once. In this case, it's basically only one quantity, the first equation. So that dn, d means change, like a small little infinitesimal change, and dt
Sorry,
means
is everyone just seeing the 6 charts? I'm not seeing the equations.
I posted I posted in the chat. So if
oh, okay, sorry about that.
Yeah, and maybe I should actually show that, because if we are recording it, maybe people should watch that. So let me switch to that. But so what are we seeing here? So it's basically the d. I don't know. Did you take any differential equation class? No, but it doesn't matter, because I'm probably want to describe these for the average person, right? So I know that it's a little intimidating, because you see all this weird sign, and some people have bad experience with math, but let me share the screen. Okay. Oh, there's still. I think I'm sharing the wrong screen. Let me try again. Yeah, this one. All right. So it's this graph, and so let me see if I can make it bigger so you can actually see it, because it's really cool, and it's going to answer your question, I promise. Um, okay, let me see if I can make it bigger. Okay, I can use this thing. Yeah. All right. So you see, this is the equation, right? Now we should be able to see it better. So what this equation means? So basically, this is I took it from an article that studied. So it was from this Chinese group that studied social networks. He studied real social networks, like WeChat and the Los Alamos preprint, with this archive where people put papers before they publish. I will do the same thing when my paper is ready. mostly to share with other scientists, get some early feedback, so then you can improve your paper when you send it to the reviewers. And there were 4 or 5 cases of real network, and the title of the paper and the main substance of the paper was, they don't follow S curves, they follow power laws. The adoption, they didn't use addresses, they had actually direct information to how many users were joining the network, and they trace it, and they show that indeed these are power laws. But they started with this equation, and this equation is a very generalized equation, because this equation allows for all the possible solutions. It can be, you can have an exponential, and all what happens is basically changing a little bit the parameter. See that little theta parameter, right? The Greek symbol. So let's try to understand this equation. I know that people are intimidated, but it's actually, you can see when you start to focus step by step on things, you can actually understand. So I'm pretty sure that people will understand it. So look at this. We are trying to describe a change. We are basically saying, imagine, for example, we do this every day, right? So that delta t, the dt, means a change in time of 1 day. So it's basically 1 day, right? So it will represent a change. And in general, when we do these things in physics, we can do, the idea of this dt is make it as small as possible, because you want to look at infinitesimal changes, right? But you can, if your data, let's say we have only daily data of a change in addresses, that dt will be day. So it's not a very difficult concept. We are saying, what is the change, because d means the change, in n. N will be the nodes. The nodes in a network are basically the place where there is some information processing. It could be, like, if you're talking about the cells in a body, because it can be understood as a network, will be the cells, and in a social network will be the people that are participating. So these are the nodes, right? The centers where everything happens, and then there are 2 things that identify a network. It will be the nodes, and then it will be the connections, right? How everybody is connected with each other, the information transfer from one node to another, etc., right? So in this case, we are talking about addresses, because it's our proxy for Bitcoin. It's our proxy for the number of users. I know it's a proxy, but sometimes you have limitation like this. We are not using directly the information, but something that is related. It's okay. It's one of the things that happens in physics all the time. Sometimes we have indirect measurements of something. I told you with the particle, we smash particle, we are trying to understand what the heck is going on inside it. We are used to that, to measure things indirectly. So what does the equation say? That change, right, that d means the change. So basically, how many new user we get every day, or new addresses every day, that is the left side of the equation. Is that understood? It's pretty simple idea, right? So that strange symbol now makes more sense. So we want to know how many new user we have every day. And the equation say, well, it's going to be proportional to some kind of beta. Beta represents the rate of change. Many new Bitcoiners we are going to get, or new addresses, if you roughly say addresses equal to new Bitcoiners, right? Then it's going to be proportional to what? To n itself, basically to the state of a network right now, how many users we have right now. It makes sense, right? Because you're basically saying we're going to add more addresses, or there will be more activity in this network, or new user, in a manner that is proportional to how many users there are right now. You see? It's really simple, but it's really the critical idea in understanding why power laws are there in the first place. It's basically an iterative process, because you see, if I want to move this step forward, imagine I'm doing some kind of a simulation where I start from day 1, I calculate the change, And then I need to recalculate that n, right? Because there is an update. So there will be two steps. I calculate first the change, and then I update n by adding the change, right? I take the previous day n, and I'm adding the new change. Do you see how it works? You see how you could make a kind of an iterative loop like this over and over again? Do you follow me, Alpha 1?
Yep.
So you will create, and in fact, this is exactly what I did. I've made a little code where you need a starting point, right? What is called initial state. So basically, I assume that at day one, there was only one. Who was this guy? Who was this guy in our case? That the first one guy when everything started with Bitcoin. Who was this guy?
Satoshi.
Satoshi. So, Satoshi was N1, right? So, and T, imagine that T represents day one, day two. We move T and we calculate every day. We could do this together one day if you are interested. Um, say, okay, then one was one because it was only Satoshi, right? Then, okay, let's calculate N2. How do we calculate N2? We want to know how many new people Satoshi was able to read the pill. And this equation tell us, right? It should be proportional to him, only one, and T was one. It will be some rate. The rate in the beginning you don't know. You derive it from the observation. It's some kind of. Now it's possible that one day we come up with some theoretical reason of what beta should be, but basically you derive it from the observed trend. You extrapolate that parameter. Now notice then we divide by t. Now that dividing by t, basically because you're dividing by t, so bigger is t, in the beginning is just one, so nothing happens. But by day two, t is two. So you're dividing by two. So that means that by day two, the efficiency of red pilling went down by two. I know it sounds crazy, but basically, for some reason, now if that is true, if that parameter theta, because that is the beauty of this equation, the theta can be any value. You have the goal of these simulations that we are going to run is to extract all these parameters. We want to know what beta is, what theta is, and that big huge n is some kind of limiting factor. So basically, this is where the wave rule comes. There will be some kind of final number of Bitcoiners when this equation taper off, because basically it allows, as a possible solution, a tapering off. And so that is the ultimate number. It could be the entire population of the Earth, where everybody adopts, but my understanding is probably it would be a fraction, and then Bitcoin becomes the standard, and then this equation doesn't work anymore, because what are we describing here? We are describing the process of adoption. Once it becomes, like if all the nation decided to adopt it, there is nothing to adopt anymore. This process ends. Everybody by basically decree will have to deal with Bitcoin. It will be part of their life. So these tell us how we go there, right? So very bit end doesn't have to be necessarily the entire population of the world. It's going to be some kind of a fraction, right? And then you see you subtracted from you subtract NT, right, the current number of user now from that n. So that n minus nt at the end in the close parenthesis represents how many people we are left to red pill. So that number on the right represents how many people we have left to red pill. And so then, see, the beauty of that having that theta is that if theta is 0, when you take t to the 0, you get always 1. So basically that t disappears. So if that theta turns out, and again, remember the goal of this simulation is to calculate that theta, to see what is the theta that best describe your underlying data. That see, in the case of a paper, they use the different social networks that we were studying. They did it for each social world networks. They redid the simulation and they calculate what these parameters were for that particular social network. In our case, we are using the addresses. So our goal is to find out what are these parameters for our particular case, which is Bitcoin. So if theta is 0, then we will have an exponential, because if you have a process where imagine that beta, in fact, I can tell you, turns out to be 3. Okay, when you actually derive it from the simulation, the best parameter that tell us it's a number close to 3, 3.1, something like that. It turns out to be 3.1. Basically, it's telling us every day we red pill, orange pill 3 new people. Okay, but if theta was 0, then we will divide by 1, and that is exactly what will happen. Every day 3 multiply by the number of people that we already have, right? So you take 3 multiply, so each of us basically in average orange peel other 3 people. So imagine if that was true, right? You orange peel all of us in average, right? So people will not do anything. Other people, if you have a big channel, they bring in more people. So it's an average thing. But imagine all of us, all the Bitcoiners existent, right? Because you take 3 and you multiply by NT, that is the number of Bitcoiners at any given time, will orange peel 3 people, right? Like a kind of almost like one of these multi-level situations, right? Where people bring in new people and kind of almost like a pyramid scheme, right? Bitcoin is not, but we are spreading the news, right? So imagine if that happens every day. Imagine how crazy it will be, right? It will go really, really fast. We will reach almost like, human level population very quickly. And we could even do the calculation how long it's going to take. One day maybe will be interesting to do it. It will take very little time. I don't know. I didn't do the calculation, but it's really fast. And it's exponential. It's exponential. What doesn't make it exponential is that theta, when you actually go and calculate it, it's not 0, it's 1. And it can be anything. It can be anything between 0, 1. It can even be bigger than 1. It turns out when you actually, because basically what you do, you run this simulation, and then at any particular moment, you compare it with the real data and you say, hey, can you extract? So there are methods where you extract the values of beta, you're extracting the value of theta. Can you come up with the best value of beta, the best value of theta, and even n? So the first result is that n, and this actually finally answers your question. The value of n is huge. It doesn't really tell you what is exactly, it's a range, but the result from the data is going to be huge. It's so big, and basically you can say it's like 5 billion people, 10 billion. Eventually, as we get more data, it will be clearer what it is. But right now, it's very big relatively to the existing number of Bitcoiners right now. So that is part of the answer that this simulation tells us, that we are in a regime where it kind of almost doesn't matter what this n is. It's huge. And so basically it doesn't matter. You could put 10 billions there, 100 billions, it will be the same, even if we don't have 100 billion. You will get a very, very similar behavior. And so it gives you more like of a range more than one specific value. And that basically says that is a huge number, right? That we are in a regime where it doesn't matter. It's almost like you can forget about a component. And then beta turns out to be close to 3, and theta is 1. When you have theta 1, then basically you are divided by t. So you see, every day, instead of all of us, orange peeling 3 people, we are on page 3 people, but then divided by how much time is passed since the process started. So basically, since Bitcoin was created. And this process becomes less and less efficient as time passes by. And that is what is the difference between a power law and an exponential. And there is basically this diminishing returns, because basically what happens, how do you go from this to price? Well, the links, there is a similar equation. We don't have to go into details, but you can write a similar equation that describes how many links there are in this network that is going to be proportional to the number of nodes. And guess what? By working that solution out and doing the simulation, you get the power law in time. In fact, you can see it. Let's see if I can. In fact, it should be in the same graph. Let's see. And I think we need to zoom out. Let me zoom out. Okay, you see now, you should be able to see the second panel. So the first panel, the black line is the information that they fed in. And so basically, I run this code, I run this simulation. Every day we calculate how many new addresses we have, and we are trying to match the result. And so we are trying, basically, the goal here is to find these parameters that best fit the underlying data, that is the black data. And the red curve is the solution of that. Notice it's a beautiful power law. And in fact, the slope of that power law, it's 3, exactly like the one that we found empirically. So this one is different, right? You understand, it's a process. Instead of doing regression, we're doing a process step by step, solving these equations and saying, okay, what are the parameters? Because we allow anything. We are not, you see, when you do the regression, you are starting, it looks like a straight line. I'm going to fit it with a straight line. Here, you don't know. You let the computer find the best solution. Say, okay, I'm going to find, it could be an exponential. If it was an exponential, it will find an exponential. If it was an S-curve, it will find an S-curve. If it was a Weibull, it will find a Weibull. It doesn't find a Weibull. It found a power law. With a question mark, let's say, the power law, the Weibull is allowed, is a possible solution, but it's not like a required solution. It's like one of it. Basically, it's telling you, okay, yeah, it could be in the future, it could become a Weibull. But the problem with that, like you asked me what I think about that, is that you don't have any way of assuming that. Why will you assume that we actually getting a Weibull? You have basically not even one solution. You have an infinite value, because it could be this Weibull, it could be this Weibull. It depends on what is that ultimate end, right? You have like an infinite sequence. So in science, we like to use what is called a Occam razor and say, I don't need that assumption. The day I have more data and I start to see some tapering off, then I'm going to modify my conclusion and say, okay, it looks like we are transitioning from a power law to a Weibull. But right now, this is why I like what he did, and we talk and he kind of agree, because it's a scientific way of doing it. He agrees with me that it's not necessary. It's not. I mean, it's interesting and it has some perspective, because sometimes people, they think, oh, if this goes on forever, we are going to have something more than the population of the world, but not necessarily, because basically, if there is some event, like basically we call it a phase transition, where some huge nation, let's say, imagine United States, decide I'm going to adopt it as my monetary system, or I'm going to peg the dollar to Bitcoin. Then everybody else follows very quickly, like China, Russia, all the huge big nations, and everybody is using Bitcoin. This thing ends, and it ends before it becomes a Weibull. So there is absolutely no reason to assume that we are dealing with a Weibull, even if it is allowed, if we can use a simpler model. You always use the simplest possible model in science, always. That is the beauty of a power law, that you go to the simplest possible model. And the simplest possible model is a power law. So does that answer your question, Alpha One?
Oh yeah, thank you so much for that.
Yeah, and then you see how beautiful it is, because you see it's a little bit more complicated equation, the following one, but this equation is supposed to calculate the connections, how many connections we have. And so basically use both the first graph, the information from the first graph, because that is going to be that nt in the equation. Then if we can zoom in the equation, just to give you a feeling, with maybe without going necessarily in the details of the equation itself, because if you understand the first equation, you understand like 90% of it. So
sorry, I just have to drop off now. Where did you share this document? I can't find it in the.
if you go in the chat, and you can get in the chat by clicking that little bubble that you see there on nearby the voice channel, then I link it there. It's in bitposeidon.com, the modeling Bitcoin growth with network theory. Do you see it? Can you see? Okay, so he left us. But basically, for the audience, this second equation, so E in this case means edges, because it's another way of talking about. Yeah. Did you find the article? Where you
yeah, I've got it now. Thank you.
Yeah,
sorry, I dropped off for a second.
Yeah.
Okay, thank you so much, Giovanni.
My pleasure. So this E. These E here are the edges. And Alpha 1, if you need to go. And we are going to record it, and you can come back and listen what we're talking about.
Awesome. Thank you.
No problem. Bye. So E is edges, right? It's another way, it's a technical term for the connection. So imagine you have this network, and then you have this connection. So basically, like right now, right? We are being connected. We are transmitting information. We are helping each other to be even more orange-pilled. We are acting as a network. And the activity of a network are both determined by the number of nodes, but also the interactions in the nodes. And so this is what the edges are. Because, you could have everybody connected to everybody else, right? And so basically, for every node, you have a number of edges that is proportional to the number of nodes. That will be crazy, right? Sometimes networks like that are very inefficient. Like if a brain was like that, you will have autism. It seems like right now a lot of studies point out towards the brain of autist people are too connected. That is actually not a good thing. Sometimes you want to prune the connections to make it more efficient. So it's not a good thing where everything is connected to everybody else. It's not a very efficient way of making a network. Many times, one of the best efficient ways, you have a lot of local connections, and then once in a while, you have like a very long range connection. Maybe you have a node that is very well connected to a lot of other nodes. And these kind of networks are called scale-free. In fact, they show basically like power laws. They look like power laws. So basically, that is very similar to what happened with Bitcoin, where you have one node that is has a lot of connection. Maybe it's a whale, maybe it's an influencer, and then you have some people that are not connected at all, or maybe they have like one connection or whatever. And so this equation describes how these edges, how many number of connections in total we have. And notice, there is another beta, in this case beta 1. So it's another rate of change of these nodes. It still has the T over theta, right? That basically tell us if we have some kind of braking mechanism, and theta is also, because we derive it also from solving the equation. Now you have to solve both at the same time, right? Theta is 1, so basically we have this diminishing return effect. Of course, the number of edges is going to be proportional to n, that is the number of nodes. And then there is this alpha. And alpha basically is some kind of parameter that determines how strong these connections are. It's modulating the strength of the connections. And then you can see that we still have the number of edges, right? Because the number of edges now is also proportional to the number of edges in the future. So this is how it works, right? And it's basically a completely different way of deriving the power laws that have nothing to do with what we did in the beginning. We are showing that we can get these power laws in multiple ways. We can do it just looking at the total data, make a I guess, okay, it looks like a straight line. Let me use a regression. Many people think that this is all what we did. It is ridiculous because we have spent so much time to doing it in different way, exploring it, going deeper. So this is a very, very powerful way of doing it because we are trying to show that it's a network, that we can derive this equation from basically creating a simulation of a network. And we derive all these parameters, and it's completely agnostic to what is supposed to be. If we add an exponential behavior, we will find it. If it was an S curve, we will find it. We didn't find it. The algorithm found power laws, both for the addresses, because you see that straight line is a power law, and it found a power law. This in the beginning, it was a little confused, right? It is a little bit curvy, but it's good because it shows we're not doing a normal regression. We're doing something more complicated, but we found the power law, the same power law. The slope is the same, everything. So basically, it looks like a network property. The price looks like a network property of a system that has to do, that is proportional to the connections, the number of connections in the network. It's a very powerful way. Now, recently, and kind of wanted to talk about that, and maybe we can spend a few minutes and then we can conclude the meeting, but I can show you these latest results. So, because I'm trying to show it in so many ways, where hopefully people in the end are convinced, yeah, okay, there is something here. It's not just like some silly regression line. It's not silly because, believe me, there are people publishing paper just on a regression line. But what I did, I did this graph. I'm going to show you in a moment. About 160 slides in this presentation. Okay, so we're going to add a new one. Sorry for the cough. I'm still dealing with COVID. All right, I'm going to show it in a moment. So basically, it's this graph that hopefully you can see.
Yeah, we can see it.
All right. So what this graph represents. So what I did, I wanted to show that the power law is something much more fundamental than just like drawing a line through the data. And so I took different data, and you can do it at a certain point. I'm going to do it with minutes. I'm going to do it with hours. But right now we're doing it with days. So I took all the days, the value of the price, and then I picked 2 days randomly. So you can create random numbers on a computer. And so I generated, I think in this one is 100,000. So I generated pairs of days. So imagine day 3 and day 329, day 5, day 234. It could be day 3 and day 4. It's all random. I did it 100,000. So it's picking up 2 random dates. It's taking the ratio of these 2 dates, and this is what we have in the x-axis, what I call ratio of time. And how do we read it? It's all in a log graph. So when we have 10 to the 0, that is 1. And notice basically we are going from basically 0. So in that case, we mean we have a small number over a big number. So day 3 over day 300, for example, 3000. So we'll give you a small number because you're dividing a small number divided by a big number. Then in the middle, basically, we have 1. I know it sounds crazy because so all these are fractions, basically, up to 1. 10 to the 0 is 1. And then starting from 1, you go all the way to about 10, because basically we have like 5,500 days right now from when Bitcoin was created. And we start to collect data at about 500 days, because this is when we start to get the exchange data. So unfortunately, we don't have much data in the first 500 days. It is close to 2 years, 1 year and a half or something like that. It would be nice if we had continuous data because we could see what happened early on, but we don't have this data. So we are talking about, if you take in the smallest amount of time from the Genesis block and the longest amount of time, you're talking about a factor of 10. So if you go all the way to the right, you get about 10 in terms of these ratios. So and then I run it over and over again. And what do we have in the y-axis? On the y-axis, we have a ratio between the price, for day 2, and the price at day 1, right? So I have T2 over T1 on the x-axis, and so basically, how much more time? So basically, imagine I have a day 500 and day 1,000. That will be a ratio of 2, right? So it means you took a day and then you went a number of days in the future that is twice the number of days that you have right now. You see, that number will be 2. You can also, it's a useful quantity because you can think about almost like a holding time. You can say, what if I want to compare how much money I make if I hold 500 days versus 1,000, or 1,000 days versus 2,000, because, or 1 year versus 2 years, so 5 years versus 10 years, right? So all these will be ratios of 2. So you're saying I'm holding this amount of time. If I double my holding time, how much more money I will make, right? How much is going to be my gain? Because you're taking the ratio between two prices, and so it's basically your return, your gain. And that is what this graph represents. We did it in a log graph. And the beauty of doing it in this way, by random numbers, is that now you are not, you don't care about the particular sequence of events that happen with Bitcoin. You're not trying to fit a line through some kind of a sequence of numbers, even if they look like a straight line when we look at how the price looks like. You're doing it over and over again at all the different scales. You're doing it on scales of days, you're doing on scales of weeks, you're doing on scales of months, you're doing on scales of years. You're doing it at all the different scales. Now, you don't get something perfect. You don't get the red line. The red line is the trend, right? Is the trend of this cloud of dots that you see, because there is randomness, right? Imagine I take a day that, the second day is very close to a peak and the first day is close to a bottom. This ratio is not going to follow very closely the power law. It's going to be like a deviation from the power law, right? So you're going to have some fuzziness there, but you can see very well, even if I didn't put the red line, the general pattern is this beautiful straight line, roughly, okay? Or at least a cloud that is stretching like a straight line over a range of sizes on the left side that is many, many, many orders of magnitude. Incredible, okay? And this is what he said. For example, see, if we wait 10 times more, imagine you waited, like you hold 100 days versus 1,000 days. The answer is that you will make 1,000,000 times more. You will make 1,000,000 times more money. And like it's a number that we use often is 2. 2 will be the second little mark after 1, right? That is in the middle. You can go there, and at some point I will show in a graph how that works. But basically, imagine you go up at about 2, and then you move on the left, right, to see what value you get, and you get something close to 65. If you go to 3, you get something close to 720, and so on. So this is how much more money you get if you wait 2 times, 3 times more. You get 65 more, 720 more, and so on. But the value of this graph is that you can see it generates the power law all by itself. Right? You can see, even if there is some randomness and some cloudiness, it's a trend. It's a very, very specific trend. It tells us that there is something very deep and profound about the nature of Bitcoin, where it doesn't matter at which scale you're looking. You can look at changes on the order of few days. You can look at changes on the order of weeks, months, years. It always, in average, follows the power law. There's something much more deeper. Anybody will say, "Oh, you just connected, you just wrote, you did a regression," and because they are very dismissive. A lot of people like that are idiots, because, like I say, even just by looking at the graph, you can see there is like a trend, there is a pattern, etc. But this like destroys any criticism, because it shows you do it this over and over and over again, and statistically, it creates a power law by itself. So there is no doubt, and I did it. I don't know if you saw the other graph that I did. I did it with addresses, you get the same thing. I did it with hash rate, you get the same thing. And then I actually even put it together. I can show you this one. It's really cool. Let me show you. Where actually I put them all together. And it's not too different from the other graphs I did, but it's a really different type of construction. And in fact, in a way, it's what a physicist will have done. I don't know why I didn't do it before, but this is very much what a physicist will do, because it's basically like you're sampling in a random fashion, and you're asking this question: is this thing scale invariant? And you're asking it basically 10,000 times, and you're sampling. You're saying, okay, independently of a history, of a particular history of this thing, if I look at all the different possible combinations of changes, do I see a pattern? Is there a pattern there? And the pattern is loud and clear. So look at this graph here, where I take addresses on one axis, I take hash rate in the other axis, I take price in the other axis, and then I'm going to make a version where I'm moving around, and you can see the different sides of it. But I did the same thing, but now with all these parameters, and see how they are related to each other. They form, like, in this 3D space, they form a power law. And the red line goes through it. So it means that it doesn't matter which quantity you look at, addresses, hash rate, price, they are all scale invariant. And scale invariant simply means that you see the behavior of each single dot in average, it's the same. And it doesn't matter if you do it on the scale of weeks, days, months, years. It grows, Bitcoin grows always in the same fashion, in average. And the idea is, and this is why this is so different from everything else, because I don't know if, how much scientific way of thinking you have in your life, but if I see something like this that has behaved over basically a change that is something like a million, okay, and it has done it for 15 years, my way of thinking is there is something underlying. I don't know what the heck it is, but there is something underlying this phenomena that makes it behave in that way. It's not due by chance. And so whatever that operated over this incredible order of magnitude, and not believe me, but understand that if we are talking about going to a million, people think that, oh, we are early on. We are not early on. We already had a 6 order of magnitude. We are talking about the next order of magnitude. So we're saying, well, going from a million to 10 million in terms of change, that change, that is just one more tick, right? So can you see, the ratio price, right? We are going to not even 8, we are going 7, right? So imagine I stand that graph where now we go to 7, right? 7 in that case will mean 10 million, right? Not Bitcoin being at 10 million, but at 10 million change, right? It is basically a million because we started with a fraction of $1. So we're talking about 1,000,000 Bitcoin. So 1,000,000 Bitcoin is a little more of a tick there. So add a few more little dots. Do you think that adding that few little dots will make Bitcoin behave in a different way? It's ridiculous. It's ridiculous. No, it's going to continue to do this thing. It's just a small little change. There is absolutely no reason to think that this process that does behave in this way, in this very, very precise manner, will change in the future. This is why it's predictive. And I repeat this so many times that people, I don't know if I don't get it. I don't know what can I do? Maybe you guys can help me. What can I do to make it clear to people? It's very unscientific to think that something like this that is so regular, so precise, so organized, with some randomness, right? Because of course, on a daily basis, it seems chaotic, it seems that it's doing its own thing, but in general, the pattern is clear. Why will it change? Why will it change? There is absolutely, like all these people, oh, the power law will break. Okay, break this thing. It's absolutely insane. People when I hear some people say, there are kids that like some of these people, British old or whatever, they don't understand anything. They're like ignoramus, like low level IQ people, not trying to insult them. I'm just serious. I'm serious. Maybe they are intelligent in their field. They are street smart or whatever. But they have absolutely zero clue about science. And Bitcoin is science. You can see it behaves in this very precise fashion that is unique, because there are no many other systems that behave like this, in particular in the financial world. You will not get this with gold. You will not get with this with SP 500. It's so incredibly unique. And at thinking that it's going to do something different in that little, you can imagine, like I can even draw it for you guys, but you can see, right? If I go from 6, that is the top of that graph, to 7, it's a small little chunk, Why will in that little chunk will start to do something completely absurdly different? No, it's not going to do that. It's going to continue in this way. Do I know 100%? No, I almost everything I know about science and etc. tells me that has to be the case, right? So I don't know what you guys think, but it's something very fundamental about the system that it will continue to behave in that way. What do you guys think? Do you have any question? Do you understand what this graph represents, how it was created? Do you have any questions about this particular thing?
If no one else has any, I have a question about how you account for the decay in that, if it's going to continue in this way. What about the decay in the higher deviations?
Yeah, it's not included here. One thing I can do on a certain point, I was thinking, like, where are the bubbles here? Because it's very difficult to see. Probably these wavy things are the bubble. We need to see. One thing I can do, because it's a little bit more complicated of graph, right? I can go back and color code all the ratios that came from dots involving the bubbles and see where they fall in the general trend. We can color code it. We can color code the bottoms. We can color code the tops. I don't know yet where they fall. Are they the largest deviation is what probably you will expect, right? But it looks like almost like there is like you could, in fact, it's something that I can do next. You can almost draw 2 other lines, or maybe even like a kind of a like cylinder. We can maybe put it inside some kind of cylinder that represents like the largest deviations, kind of maybe we can draw a semi-transparent cylinder representing the largest possible deviations. And so you can see that everything happens within that little cylinder, and then color code that, what are the bottoms, what are the tops. So it does, here, it's not that I did anything, I just plotted see, but a lot of what the people don't realize, a lot of these graphs are not like some kind of complicated calculation. I told you exactly what I did. I took a ratio between 2 dates, I took a ratio between 2 prices, and then I plotted them. Like it's not really even a model. What are you talking about? The model is maybe me drawing the line in between, say there is a line. You can call that the model, but I probably could get it even by averaging the dots, right? And that will be also another observation. Just average the dot and you get a straight line. I mean, it's an observation. You can see there is a very precise, organized pattern. Now, where the bubbles are, I don't know. Like I say, we need to explore that. And I don't know if there is a decay. Maybe the decay of the volatility. Because these are all the good questions. Like when you make these things, and you start to ask the questions, and you can start to explore. You see how it looks almost like a fuse. And so as you come closer to large ratios, it starts to look like it's tapering off, right? The variations from the straight line seems to become smaller. Now we have to measure and see if that is really the case, but this is what it seems, right? And that could be basically what we observe, that over time the volatility is going down, right? That decay that you're describing. So it's becoming, actually, if anything, it's coming closer and closer to that red line. It's becoming more regular, more precise. There were more variations initially. Um, so it's a little bit more difficult to think about this graph, because remember what this thing represents this ratio, right? So a ratio of addresses, so going to change addresses from one particular value to another value in the future. It goes actually in both ways, because this is why you get negative values here, because in that case will mean you start with a very high value and you go back in time, right? And then also the price will go down in time. So maybe I didn't need to do both directions, but it's still cool, because you can do it moving forward in time, moving backwards in time. But the scaling works in both directions, because you're going down with time, but you're also going down with price. So it stays basically the same, the ratio between these two things. So it basically is telling us it doesn't matter what you're looking at, addresses, hash rate, price, all of them scale in a very proportional fashion. And it's undeniable. You can look at it's like there is no really modeling of any kind here. It's just drawing the data, right? And there is the fuzziness, there is the and also this intricate. You see how they kind of wave around. It's almost like there are these kind of weird waves all around each other. It's really cool. It's very complex behavior. Tell me again.
Like a coil, like a coiling.
Like a coil, right? It looks like a coil. But
That was my
again,
other question.
yeah.
Yeah, that was my other question, is how do you model it so that it's in like a 3D space? Because if you think about the way that, I don't know, just for me thinking and looking at this, I think about the solar system and how it's like it goes in a spiral, it doesn't go in a straight
Right.
line. So it's like this
Exactly.
relationship. So I'm just curious about how it is that you model this pricing with Bitcoin and the power law in
So
3D space.
basically, when you're doing 3D, you're going to have three. Basically, every dot is expressed by three numbers, right? X, Y, and Z.
Yes.
Yeah.
Yes.
It's almost like you're describing the position of an airplane, right? You will need the X, how far is from the airport, in the east, west, west-east direction, how far it is in the north-south direction, and then the altitude of the airplane, right? That is your Z. So in this case, the X will be the ratio of the addresses, so basically how big the change in the addresses is, how big Y will be your change in hash rate, and your Z, basically the altitude, is the price. It's conventional. You could move them around. Doesn't nothing tell us we should put price in the Z-axis. But it's kind of cool because it gives us a feeling of the growth, right? Of the growth of the price over time.
Right.
And time is implicit, right? Because if we had a fourth dimension, and we could visualize a fourth dimension with we cannot, we could put also time and see how this, but time is kind of implied in the sense that as you go towards higher prices, it's longer and longer time, right? Or at least ratios of time. So this is how you do it. You say, okay, I have already calculated these x, y, and z, and then you have a function called scatter. Do not scatter tree. It's a function in MATLAB. This is what I'm using, and he knows you want to represent something three-dimensional, so it draws each dot at these coordinates, right, where you're going to have an x, y, and z, and this is how you do it. Now about the red line, basically I made when I did individually each graph, um, I made a fit, like in that case it's a regression. You're trying to find the best line that goes through the points, and I did it for each of them separately. And then I do the same thing. I say plot them as one single function, and this is what you get. You get the line through all of them. So basically, it's like a super power law that describe how everything scales and how everything is related to each other. That these parameters are intimately related with each other, that one influences the other. Now, which one drives what? There are methods to do that, like different techniques that basically shows which signal leads what. But in general, you will think it's some kind of a feedback loop, right? Where
Right.
addresses grow, that makes the price go up, that makes the hash rate go up, and this is why you have that kind of twisting and twirling, because maybe sometime one quantity leads the other, and then the other one does, and it's really, I mean, if you are not in awe by looking at this thing and thinking Bitcoin is really a
It's a
freaking,
living organism.
it's like a living organism. It's like something very special, and this is what I'm trying to communicate. And some people hate me. I don't get it. Why they're so hungry about it. I don't know why. Something's weird psychologically. Besides, maybe that the growth, according to them, it's slow, right? So because basically we are saying that going up by a factor of 10, so going from 100,000, more or less where we are now, if you think scale, because you always round to the next 10, right? So saying 60 is the same thing than saying 100. This is how you do this scaling thing. You round it to the next 10 number. So basically we are close to 100, and now we want to go to 1,000,000. How long is going to take? The graph tells you it's going to take something on the order, because it's another basically order of magnitude in time. So another order of magnitude in time means basically the same amount of time that we have right now. I know it's weird, but it's scaling. So basically we're going up by 10 over a scale that is similar to the one that we have right now, that is about 10 years, right? 10, 15 years. It will take another 10 years to reach 1,000,000. And they don't like that. I imagine that is a huge component of the hate, because they would like something faster and, be millionaire tomorrow instead of waiting 10 years, I imagine that, because otherwise I don't get it, because will you rather have something that can do anything, because it can go up, but it also can crash, right? We never talk about that. So if you want something wild and crazy and you can do anything because you don't like that it does something regular and precise, then we rather have something that can go crazy in both
Yeah,
directions.
that would be like the equivalent of death at that point. It would just the thing would just die. Like
Yeah.
Yeah, something
it would break.
seriously wrong in the world.
Yeah. It would just be like a
Or
total
illness, right? Illness. Because I have this graph. I can show you. I
What
have
I
this.
would also recommend people to, maybe you can also speak more about it to your followers, is to reference Jeffrey Westmore and his book. Like I've been
Yeah,
reading it personally, and it's been really enlightening.
yeah, it's an amazing book, right?
It really is. He
Um,
talks about all of this stuff.
yeah, and it's so well, in such incredible, engaging way, and also meaningful way.
Mhm.
Um, but basically, the graph I wanted to show you is this one, right? Okay. So what this graph represents, it's from this article that by the way, if you guys have a chance, read it. It's a
Maybe
little
search in.
technical, but it's not really too difficult. And there is also a version that is a little bit more popular, like they trying to make it simple for people. Let me adjust the
Yeah, I think it's zoomed in a
magnification.
little bit.
Maybe it's out, right? Okay.
Yeah.
So what this is from this article. The article is actually this one, a universal power law for modeling the growth of form of teeth, claws, horn, thorns, beaks, and shells, right? Talking about living organisms. So these guys basically discover that all these things grow like power laws. And there are two power laws. There is a so if you look at a tooth, right, there is the radius and there is the length of a tooth, and the two kind of almost like here in this graph where hash rate interacts with price interacts with addresses. It's the same thing. They interact with each other, and so one imagine there is power law growth in the radius, there is power law growth in the size, and they form basically almost like a twirl, maybe like some kind of, it's called helix. It's an helix. So basically, like this kind of planets orbits, right? You say when you look at them in 3D, they do the same thing,
DNA.
and it's incredible, right? It's beautiful, and they can create, and they can actually, according to the ratio, how fast one grows relatively to the other. We can get shark teeth, they can get horns, they can get thorns, they get dinosaurs, different, and different species have different ratios. It's almost like you can identify and say, oh, measure the ratio between this and this. Oh, this is this dinosaur. This is what this was. This other. It's a shark, and this is this other thing. It's incredible. It's beautiful. I mean, if you are not fascinated by something like that, I think you're not alive. And Bitcoin belongs to these kind of things because, again, the different ratios between how hash rate grows and price growth determine the overall growth of a system. So here we focus only on one of these quantities instead of both at the same time. So here we have radius on the y-axis and we have time. And so these are elephant tasks. One for the female, that is pink. The other one is blue for the male. You can learn a lot of things. First of all, why the elephant male it's steeper. Well, they have a huge task mostly because they use it for it's probably due to sexual selection. They fight with it. They decide. The elephants use them in practical manner to basically kind of uproot trees. They eat the leaves of the trees and they put them down and they hit the tree, or they do other things, with them, defensive, etc. But the males, in addition, they use it for fighting against each other, right? So there is a selection in making them bigger so they can fight better. But this is why it's steeper, right? The slope is steeper. Plus, you can recognize it. I don't know if you already start to learn some of these things. It's a log-log graph. Why is a log-log graph? Because you see how the thick lines are not equally spaced. If they were equally spaced, we were dealing with a linear graph. But we are not, right? So that is actually a sign that we're dealing with a log-log graph. So we are taking the log of age and the log of radius. And we know already, because of all the things we discussed so many times, that if we see a straight line in a log-log graph, it's a power law. Now, is it a perfect power law? Notice how in the beginning was not, right? It took some time to actually found this path. I don't know why the female didn't do the same thing. Maybe they didn't have data for the beginning. But in general, then you can draw a straight line. All the people will say, oh, you're drawing a straight line. Yeah, this is how people do it in the published papers, because this is how you do it. You draw the line. It's not even a question of, you're making a simplification. You say, look, I don't know what this wiggly crazy line is. It's complicated, but roughly it looks like a straight line. So the beauty of doing that, you can then measure the slope. The slope tells you the rate of how, the power basically. I don't know what it is here. But this thing grows, like if you were plotting it in a linear graph, it will look like a J. it goes faster in time. I think it depends how, if it is a positive, if it is a bigger than one or smaller than one. I don't know. We need to look at the paper, but it's a non-linear process. It changes with time, um, and the beauty of it, it's predictive because you can look at 5 years or 10 years, and then by the rate you can extrapolate it because it's a scale invariant process. What does it mean? It means that if we did the same thing, like the graph I sampled different times, you will get something very similar to what they did. It means that no matter what, like you can take changes on the order of few years, changes on the order of a decade, it always grows at the same pace. And you can extrapolate it to the future. And in fact, kind of what you were saying, if you see now, okay, it's the elephant maybe had more food, so it started to grow a little bit faster than the general trend. Or, there are things happening to the body, like it's not perfect. It's a machine, but there are variation. Maybe it has to do with the temperature. Maybe it has to do with different growth sprouts with the animals was going through. It's biology. It's going to have you know some randomness associated with it. And maybe there was less food. Plus I don't know if this, and again I need to go back to the article. I don't know if this is averaging over many animals, or if this is one individual. It's explained in the paper. I don't remember. But even if it was just one individual, it could be like, maybe that period when it went below, maybe there was less food available, so it was okay. It was not too weird. It recovered, Imagine it deviates like crazy, too fast or too slow. Something is wrong with the fucking elephant, that is what it means, that it's not right, that whatever process is regulating the growth of a task of an elephant is not working fine. And so it's a sign that something is wrong with the system. And that, to me, applies with Bitcoin. All these people that insist that the power law is going to be broken, etc., they don't realize that if Bitcoin did this thing for 15 years, it's probably because there is a very good damn reason, and it's the best possible thing for Bitcoin, because otherwise Bitcoin will not have done it. If we really believe that Bitcoin is this amazing system that has all this, internal intelligence that is, is doing it, the right thing, etc., then if it does something different, radically different, something is wrong with Bitcoin. And I don't get it, why these people don't get it. It's so obvious to me. It's so obvious. So I don't know. I think maybe they are not really thinking scientifically. They are thinking in a very selfish way. It is not based on anything. Like I want Bitcoin to go $1 million. Within 2 months. These are what I wanted, and this is why I want the power law to be broken. It's the only reason. It's the only reason, because otherwise you realize there's something incredible here going on that regulates how Bitcoin is transforming itself, how adoption is happening, how the increase in hash rate is happening, how the price is changing, and it's all happening in this very beautiful, coordinated, interrelated, organized fashion. And to me, this is the most important thing. Every Bitcoiner should look at this graph and post it in their room and say, this is what Bitcoin is, And anything else is noise. Is noise. Because I see some of these interviews, with these influencers, and let's talk about Bitcoin growth. Okay, yeah, let's look at this graph and let's talk about it. But do they look at the graph? No. They make up stuff. Like, the day that these banks will come in, when that is going to happen, how big the change is going to be. They have no clue. It's all improvised. It's like storytelling, that can be entertaining, but has zero information in it. While this graph tells the entire story. Yeah.
Sorry, I got a question. So
yeah, absolutely.
You mentioned that sometimes like there's patterns that or moments that might be super irregular to the pattern of the power law. there's nothing that's, went outside like the regular standard deviation, but like for something that kind of was an irregular event for the power law or for Bitcoin itself was like May 2021 when it was like a ban on mining in China, right? And so what that kind of tells me is that, if there's instances like that that does affect, the
But how
intrinsic
do we
value.
know? How do we know?
Yeah, it's
That is
not
what Plan
predictable,
B
right?
said,
And
right? They say that.
at the end of the day, kind of it still followed it like after that, right? But
Yeah.
the point of what I'm trying to say is that like what this chart shows me is like the intrinsic value of Bitcoin, right? And it seems like, like obviously hash rate, like if there's an effect of a hash rate, right? Over time it'll probably go back to a pattern. But if there's like a huge impact of hash rate, like banning it in the US, for example, right?
Mm-hmm.
It might deviate a little bit from its regular pattern, right? Like how it's
Right.
happened before. Would you say something like that?
Yeah. So this is my best understanding, right? And you have also to get this. I'm not the ultimate truth, right? I'm trying to explore these things with you. And when I say these things, you have to understand them. I'm thinking aloud, and then sharing with you my thinking. But at least it's based on something, right? It's based on some logical and consistent. Because the first thing that you want anybody talking about any topic is that this at least consistent, self-consistent. Does it follow a logic that at least is coherent, And then if you can add to that evidence, and make it's still storytelling, but now it's storytelling supported by information, right? And we can learn something from it. We are not just making up stuff. So one of the example. So I don't know about China. I know that many people maybe this was this deep here, but was that deep? I don't know. We can go back. But one that I know, one extraordinary event. There is this terminology. We call them black swan. Mostly, I think, because black swans are very rare, right? They happen, but they don't happen often, and this is why they call them black swan. I'm pretty sure that is the reason. Uh, Plus, probably there is some superstition about black things, being bad or something, some stupid superstition like that. But these are called black swans, like a very rare event, large events, sometimes basically unpredictable. They are not unpredictable because if you look at, they are called distributions, right? You can basically make a graph of how likely something happen, and according to their size, you can do it with earthquakes, for example. How many large earthquakes there are relatively to small earthquake. You make a very nice graph like that. And by the way, it's a power law. There are other type of distribution. They don't have to be always power laws. And so you can look at how rare a very, very, very large deviation is. And the point is, even if I tell you, okay, a large deviation like that will happen once every 1,000 years. Okay, but then it happens. That is the problem, right? And they say, well, it happened, but it's very rare. It should not have happened because we should have waited 1,000 years. Well, but it can happen at any time, right? It's just that probably you will not get another one for another 1,000 years, but in theory, it could happen after 300 years. It's just a statistical thing. You will have to wait for so long. This is why it's nice to do it in this way, where you do simulations and you do it thousands of times, because in that case you can see, many of these very rare events, you can actually count them, given the statistics. But the point is, they can happen at any time. It's just they are rare, but they can happen. So one black swan event that everybody will agree that it was rare and very dramatic, it's COVID. And you can see from this graph that hopefully you can see, right? I'm sharing it with you guys.
Yep.
It shows COVID, that drop. And notice what happened, right? A few things. First of all, it went to that support line that we mention all the time. It didn't cross it, or it crossed it very quickly, and then it came back, right? So it was almost like a stress test for this idea that there is something very special about that bottom line there, because even with a black swan event, we didn't go below that, or not too much. And then notice what happened. Yes, it changed dramatically the trajectory of the price, but then it recovered, right? So there is always some kind of rebound, there is some kind of correction. So the way of thinking about these, along the lines of what you were saying, is that yes, locally we can have drops, we can have changes. You can see some of many of these little drops you see there in the price, right? Are they associated always with things that are happening outside? No, because do you remember when I did these simulations, this Monte Carlo? I don't know if you saw them. You can take the stats and then make like a fake Bitcoins history. You can repeat them over and over again, like 1,000 times, 1,000,000 times, and you will see sometimes behaves you like that. Like it's really weird. Like you see one of these history where the price went down, went down. It went really crazy, bad places, and then it did recover. But imagine if that happened in real life, people will start to see, oh, this is due to that and this other. In my computer, it didn't was due to anything. There was no China, there was nothing. There was a drop, and it was simply due to the sequence, right? So it's very unlikely that you get a bunch of tails, right? But it could happen if you do it enough time. There is a possible parallel universe where you get 7 tails coming one after another. You will have to go to many different parallel universes, but there is one where that happened, where some crazy guy was lucky and he bet $1 million that he could get 7 tails after one after another, and he got it. In fact, there is a universe where there is one with 15 tails, one after another. It's not impossible. It's very rare, but not impossible. And so, just by chance, you could have a situation where you have a bunch of negative, like losses, and it looks like a huge big drop. It could be just due to chance. But many times there are things like in this case, it was due to COVID, okay, or maybe China does something. The price response local. The language that we use, we say locally. That means like temporarily. It means just nearby, and then the price recovers and it does its own thing. And so this is why it's important to look at the general trend, the general behavior, because that is clear. There is a pattern there. So even if, in fact, one way that you can think is that these bubbles themselves are these deviations, right? So there are times where, for some reason, maybe again because there are reasons. I don't think it has anything to do with these supply shocks that some of the influencers talk about. It's mostly like we even made a video about this. It's a time where there is basically a renewal in the in interest, because there is a halving, miners buy new equipment, people start to talk how significant this event is. It brings newspapers are talking, there is more activity in the media, the social media. It's a euphoria. It's almost like everybody does a bunch of things that you will not do during Christmas, right? You buy gifts for people, you spend more money, you prepare for this big meal. It's like a social thing. It's like a ritual in a certain sense. And so there is a lot of euphoria. It pushes the price up. We leave the general um, trajectory and even the power law behavior. Basically, I did some study where I show that right field, please mute yourself because there is a lot of noise. I'm going to mute myself. Okay, so there are sorry for that. So during these times, when we have these bubbles, the price looks very much exponential. It's not perfect because you see, for example, for the second bubble, it went up like the first bubble after the halving of the second bubble in total, it went up very quickly, then it corrected, it stayed flat. When it's more complicated. So, but in general, this very fast growth, it looks like very much like an exponential. Um, so it's very different behavior from the power law. But notice what happened. We go up 1 year, we reach the top, we go down. The go down is much more regular in general. It looks like exponentials. And so we go down very fast, and we go back to the power law almost perfectly. You see these blue dots that basically are a certain percentage, certain percentile. You can do it in different way, but basically are dots that are the one that are closest to the general trend. We call them inliers, and the other one are outliers. So the black dots are basically like exceptions, are the deviations that are so big that are exceptions. And the cool thing that they cancel each other. Eventually they go back to the general path. And so you can even think about these ones as, okay, we deviated from the trend for whatever reason. There is some real reason associated with whatever the halving mean to people. But then we correct it ourselves and we go back, because the general trajectory, the general trend is very precise. Now, why that is so, I don't know. We need to, this is why we do science. We start with some observation, we see some patterns, we see some regularity, and then you go deep. I bet is also explained in the book Scale, because they start with describing this metabolism scaling, right, between the body of an animal and how much energy the animal uses. And then there are entire chapters where they go deeper and they start to say, oh, it has to do with the flow of nutrients in the body, and when the body has these intricate patterns that are almost like four-dimensional, not quite like 3D, three-quarter instead of being four-dimensional. All these things, like you go deeper and you start to understand the causes, the mechanism, why these things are related to each other. You're trying to understand better what is going on. This is where we need more research. We can explore Bitcoin like a scientific topic and trying to understand why this scaling behavior, what is going on, what makes because it's unique. Like there is this Matthew guy, I don't remember his name, his full name, but yeah, he's like one of these influencers that actually he kind of almost discovered the power law more or less when I discovered it, like just few months later, because I started to talk about power laws in Bitcoin in 2013, but this particular one between price and time, he discovered it, I think, in December. I did it in September. And he talks often. And one of the things I like about what he does, he tries to make it much simpler. Some of the things I talk about, he tries to talk more directly to the general person. But he always compares, like he has all these graphs where he compares how the stocks behave, how SP 500 behave, how gold behave. And he always talk about how they don't behave like by Bitcoin, because Bitcoin follows the power law. It's so unique. It's only Bitcoin that does that. And so there is something special, whatever is happening there, that is regulating, maybe because there is a difficulty adjustment, that these systems don't have. It's something very unique. It's almost like a regulatory mechanism. It's almost like a brake. It's like you have this car, and the car has brakes, so it works. While the other systems don't have brake, they are completely unregulated. While Bitcoin, it regulates itself, and it's a good thing, because a lot of things in life, this is why you see these power laws they grow, but they do it in a way that is sustainable, right? And that is what there is often behind these power law patterns. There is some kind of mechanism that allows the growth, but it also makes it more sustainable, more regular. And sometimes that means you need to slow down things. But it can be a good thing, because if you imagine, the fact that Bitcoin needs to absorb more and more cash flow and more investments, more infrastructure, more involvement, from more people. It needs to do it in a way where it doesn't crash. And sometimes means slowing down, right? But it's not really slowing down. It's our brain that looks at it like it's slowing down, because if you change your perspective and you focus on scale and say, well, this change in scale is the same. This is why we call it scale invariant. If you look, yeah, it takes longer, but simply because we are going up a factor of 10, And so if these things needs to grow and become huge and bigger, and I need to move, it's basically the difference between moving a little stone and moving a huge big mountain. Of course, when you're moving big mountains, it takes longer time, of course. And if you do it proportionally, then you see the utility, because you should start to be less selfish, because you want at any cost to be a millionaire, and you want to happen fast, and see it like something that is good for mankind. So if you switch your perspective and say, look, I'm still going to be taken care, because this thing anyway goes to 1 million, goes to 10 million. I'm going to be okay. But it's okay, but it takes longer, because it's good for the system. The system will not crash. It will be more sustainable. It can resist to, it can be more resilient to things like COVID. If there is like a crisis, if there is a banning, Bitcoin will find its own way. You see how to think about this thing. I would like to people to start to switch their thinking towards this way of thinking. Like, it's not just about what I get out of it, but what is good for Bitcoin in general, and what is good for mankind. Because these are some of the things that people say, but then they don't act coherently. They think they are these lovers of Bitcoin, but a hater of the power law, when it should be the other. If you really love Bitcoin, you should also love the power law, because it's first of all, is what Bitcoin is doing. So if you, by denying the power law, you're denying Bitcoin. Bitcoin has done this thing, So if we are humble, they think I am the arrogant one. It's the other way around. I'm telling you what is happening. I'm showing it to you and say, can we learn from this? This is what Bitcoin has done. So maybe there is a reason why it's doing it. So it's really, really, really. I know that sometimes I get emotional. I get to fight people. I can be, I'm insulting them or whatever. But it really, really, if you start to think about it, it's really absurd. It's really absurd how they react or they think about. They are in the wrong. They are on the wrong side of history. There is absolutely no reason, no doubt about that. Eventually people will look at this thing and how people reacted and say, oh, these people were crazy. They don't know what they were talking about. Of course, it's the right way of thinking about this. There is this incredible system. It's doing its thing. It's growing, and it's doing it at the right pace. It is the right pace for achieving this. So do you guys do you follow what I'm saying? Does it kind of make sense? Is it? Is
Mhm.
it?
Yeah, I posted something in the chat that you may want
Yeah.
to read. Maybe we can go over it together. It reminds
Yeah.
me of a
Sure.
theory. It just reminds me of a theory. I meant to mention this earlier on, but yeah, it just reminds me of this theory that Terence McKenna found in the I Ching, which is like this ancient Chinese oracle system that uses hexagrams, and he
Yeah.
basically found that there's this novelty wave that basically accounts for like novelty throughout history and time, and it kind of he maps it out in a very interesting way. But yeah, just kind of read it over and spend some time on it because I
Yeah.
think
I
that's
would love it. I spent when I was in my more romantic times, when I was a teenager, etc. I was in love with the I Ching. I was using
oh
it almost every day.
cool.
I was very fascinated by Eastern philosophy, and I was studying all kind of things like that. And I was playing with I Ching. I think, I don't think that there is some kind of, magical influence. It's mostly like consciousness. It's like as a way of reflecting consciousness. Like we like symbols, like our brain works with symbols, etc. So, but yeah, I'm sure there are patterns like these in nature and human society. So yeah, I would like to read it for sure. Thank you for
Yeah,
the
spend some time on it because I feel like there's some. I think basically what he found is there's also like this decay nature that he found in
Uh-huh.
it. So it just reminds me of what it is that you found in Bitcoin. So
Yeah.
it's just
And
there's a
we can,
strange parallel that I find very uncanny. So
yeah. We can, I can read it, and then if it is something, I already see that there is something very interesting connections, and maybe we can make a post. I'm writing a book,
cool.
and so anything like this that could be interesting and useful could be
Yeah,
integrated
I'm just really curious
in
if
the
you could
book.
maybe or parse anything interesting.
Yeah, seems very
I'm sure you
interesting because I these are no new things, because people have noticed these kind of things before.
throughout history.
Different,
Yeah.
and there are different historians that talk about the like Nietzsche was talking about the eternal return, right? There are these cycles where basically they are happening over time again and again. And this is one of the reasons why it's very cool to study history. I love histories,
Yes.
because you can find parallels to things that are happening right now. If you want to understand what is going on in Palestine, if you want to understand what is going in Russia, you want to study history. You want to understand why these things are happening over and over again. Everything is connected. And unfortunately, I know that there is a lot of sometimes anti-intellectualism, in particular in the United States, but it depends how you do it, because I know probably it has to do with how boring some teachers are, or how like formal education doesn't go really to the most important things, and they want to force certain way of learning. Because like, for example, we have this um, amazing guy. His name is Barbero in Italy. He's a professor of history, but he's so eloquent, and he's so like, he takes different times in history. He specializes in the Middle Age, but he's very like kind of rounded intellectual, so he knows many things, and in particular in history, he will take any time in history. Like it talks about, for example, how Italy became independent, all the wars that we had to do to become a nation. But the beauty of what he does, he will go and find the letters of a soldier, like a little soldier in the trenches, of a general, that was planning the battle. And then he will read these letters and put them in a context, so he kind of connects all the dots. All this happened. This is how people felt at the time. It almost makes you feel that you are part of that history, that is live, it's meaningful, and you connect it to what is going on right now. It's amazing. Like, I don't know, certain people are very talented like that, and like, he's like a superstar in Italy. Like, people invite, like young people, they go to a lecture that we will never have gone. Like, okay, who cares? Like, it happened 200 years ago, and they go there and they treat him like a superstar, like if he was um, a rock star, something like that. And they go and listen to these lectures. They're really excited about it, and so because this guy has this incredible ability of making it meaningful. Like, imagine if we all had teachers like that, right? In any field, like in history, math, science. Everybody will be super excited. I don't know any equivalent like that in United States. You don't have, like, in particular history. You don't have anybody like that. But yeah, so if you start to explore these things, maybe people like maybe like they were more in the 60s and 70s. McKenna, he was great, right? He was an amazing guy. Alan Watts was another, another field, like more about philosophy and things like that. So it's not that United States never had people like this. They had. It's just they are relatively rare, right? People like these that are
Rupert Sheldrake as well, and his
yeah,
morphokinetic theory.
right. And like system thinkers, and people that go a little bit outside the common way of thinking. They challenge the status quo, and they see things in a different way. these are very precious people, you know. So if you find videos of these guys, etc., learn from them, etc. But you know, this is what I in my little, I'm trying to do that. You know, I'm not always great, you know, because I have my own problems. Maybe I'm too emotional, I'm too naive sometimes in how I interact with people. But I'm trying, you know, I'm trying to go in that direction. I would like to improve my communication skills, my um, you know, ability of teaching science, or it's not even teaching, you know, it's mostly like sharing, you know,
Right.
sharing my passion. Because I was like that since I was a kid. If there is any quality that I have, is that for some reason, since I was a little kid, I was like so passionate about basically learning stuff. You know, I started with stars, astronomy, etc., and it never ended. You know, and it's cool. It's cool because you know, it's great, right? It's great to learn things, understand the world, and it motivates us, right? And this is why we feel this passion also for Bitcoin. It's not just about money and, uh, and and freedom. It's also about learning things. You know, we want to understand better the world around us. Bitcoin forces you to learn about finance. You know, things that I would never have explored myself. You know, because I thought, oh, finance, and it's boring. Who cares, etc. But you know, then you start to study and say, oh, actually, it's pretty cool. It could be interesting. You know, if you do it in the right way. So hopefully all this makes sense to you guys. It's great that you joined, and so we can share all these things. And we made a recording. Anybody has a problem if we post this online? Because you know sometimes people want their privacy, but you know it's all anonymous names. So we're going to post it online so people can also learn from something from it. Okay, all right, great. Thank you very much. Next Tuesday, we can sometimes keep it free like this and discuss you know, relevant topics. But I'm planning to do more structured lectures about the book scale. So if everybody wants to get a copy, and then you know, I can do my like mini lecture. I can introduce the topic, so it will give us some structure, and then we can leave like, you know, 15, 20, 30 minutes for discussion. You know, we can go back and forth if you like that format, right? So we can do that starting next Thursday.
Very
Sounds
good.
good.
I'm reading it currently.
Okay. All right. Thank you so much, guys. See you soon. And thank you to be here. Bye.
Thank you.
Take it easy.
Ciao.
Bye. Ciao.